Hi, everyone. I'm Vincent Cohen-Addad, and I'm going to talk about a new result called on 2 plus epsilon approximation algorithm for metric median. This is a joint work with Fabrizio, Oyong, Chris, and Ola, and it will be presented at STOC25. All right, so in this talk, we talk about K-median, which is a clustering objective, which has numerous application in reality, where you want to do clustering of diverse objects. It's a popular solution for unsupervised classification in machine learning and various other places or data mining use cases. And so in this context, we want to study the complexity of the problem and define good approximation algorithms. So in the K-median problem, we're given n clients, so endpoints, and a set of possible places to put centers or facilities, and then a distance metric between the clients and the facilities. Okay, so this distance metric has to satisfy the triangle inequality, and the objective is to find a set of k facilities or centers, the same name, so as to minimize the sum of the distances from each client to the closest facility. Okay, so this is our objective for today, and the goal is to find the best set of k elements in the k centers in the metric. Okay, so on the line, it's a very easy problem, like we have all done it in high school. We just want to compute the median of points in the line. It's simply the median of these points, right, of these values. So that's very simple. But then as soon as you move to the plane, then the problem becomes NP hard, and then we need to turn to approximation algorithms. Okay, so there's been a lot of work on K-median. It's a problem that's been studied for more than 50 years, so it's pretty there's pretty broad literature on the problem. But a very nice approach that was pioneered by Jen and Tazirani in the early 2000s was to relax the hard constraint that we can pick exactly at most k centers, but simply penalizing if you pick too many centers. So what they looked at is what's called the Lagrangian relaxation of the problem, where you will not have a hard constraint on the number of centers, but you will just put a price on the number of centers on each center, so that if you want to use it, then you have in your solution, then you have to pay for it. So it's turning the problem of the K-median problem into the facility location problem, where in this problem, we're asked that if we have a high price on this, in this problem, you need to minimize the sum of the distances to each client to the closest facility you pick, but you also need to minimize the price plus the prices of the facilities that you select. Okay, so in this context, we are going to be putting some money, some amount of cost on each center, and then if you put a high price, then if you optimize this objective, you will have few centers. But if you put a low price, then you'll have many centers. Okay, so this is a way to smoothly interpolate between, smoothly play with the number of centers as you increase the price. Okay, so here's the approach that was pioneered in the early 2000s, where we know how to do good approximation for facility location. And so in that context, one could input some price, obtain a solution with slightly less than k centers, obtain a solution with more than k centers. But these two prices are for these two solutions are extremely close, because you can continue and do a binary search to find the right value, the right price. And then once you have two solutions that are sandwiching k, then and that have almost similar price, then you can nicely round them. What's called a bipoint rounding, because you have two solutions that are combined together, give you exactly k centers in a nice way. And through that process, you will first run a 3 approximation to obtain a Lagrangian multiplier preserving solution for facility location. And then you will use this bipoint rounding and lose another factor 2, and that will give you a 6 approximation for K-median. And of course, there was a lot of work on this approach, and one could indeed improved that further. So, more people worked on it, and they managed to push the Lagrangian multiplier preserving solution for facility location down to a factor 2, which is almost tight, because the best one can hope for in that context is 1.73, and then push down the bipoint rounding to something tiny, 1.3 or something, and then one can go down to roughly 2.6. But we're a little bit at the end of this road, of this research direction, because okay, we can lose a factor 1.99999 for this, but like we won't be able to go much farther than that. 1.73 is the limit for the Lagrangian multiplier preserving, and the bipoint rounding we have managed over the last 10 years, 12 years to go down from 1.37 to basically 1.3. So in that context, we just go down to roughly 2.6. And so we were stuck there. And the main idea that we have in this paper, which is not the, it's a natural idea, is to try to do these two steps together at the same time. Like, don't separate the Lagrangian multiplier preserving solution with the bipoint rounding. So of course, it's way more technical to do it together, but it's also a way to maybe not lose the two factor together. And actually, this is something that this idea was started back in like 2017 with some work on k-means, where in that context, they wanted to get a good approximation for k-means, and they took the same path, but basically they observed that that this was a pretty good path for k-means, where if you have some kind of well-structured algorithm for facility location, then you can round it. The bipoint rounding could be done while using a 1 plus epsilon approximation. And so that was very nice, because it was basically, we were able to, in that paper, the authors were able to really round without much loss, and that gave us the hope. And you can see that in all our slides from 2017, they were hoping that this could actually get us a 2 plus epsilon approximation for k-median. And so this is what we do in this paper finally. All right, so there was a lot of work on k-median. I'm not going to go over all the details, but basically we started log n in 96, and now we're down to 2.61 from last couple of years. But there was like a little bit stuck from last 10 years basically, and so we are happy to make a little bit of a progress here. We've been going down to 2. Okay, and our result breaks into, is divided into 2 parts. Like, there's the first part, which is a 2 approximation for k-median, but that opens more than k centers. It actually opens k plus log n over some poly epsilon centers. And we have a second theorem that says that, well, if you have an instance where decreasing k by 1 increases up by a little amount, then we can show a 2 plus epsilon as well. So these are 2 complementary algorithms. And so the main idea then is that, okay, well, either you're in a case where you can actually remove log n over epsilon square, epsilon centers, and the cost doesn't change, in which case I'm going to run this algorithm with a new k, which is k minus log n over epsilon, then solve it with theorem 1, have extra log n over epsilon centers, then I'll have at most k centers, and I'll be happy. Or you're in the second case where, if you start removing centers and the cost starts to go up, then you are actually in these specific instances that are often referred to as stable instances. And in that case, you can use theorem 2 that says, well, now if you start removing too many centers, then you're in a scenario where your cost increases, and so we know what to do. All right. So there are few ideas that are mainly mentioned. So yeah, 2 main components: pseudo solution with more than k centers, and the stable instance algorithm that converts this. Cool. So let me give you a few ingredients, theorem 1, theorem 2, and then a summary and open question. So let's go into theorem 1. To understand theorem 1, you have to understand the Jane-Vazirani framework for getting Lagrangian multiplier preserving solution for facility location. In that scenario, you have clients, and each client, all the clients are growing a budget as time goes by. So you have a notion of time. As time increases, the clients increase their budget until they are happy. As long as they are not happy, they increase their budget. And so you can see here, if we assume the radius is basically the client's budget. So let's assume the budget is 3. It corresponds to this ball of radius 3 in the metric. And as we continuously increase the radius. And what does this budget mean? Well, this budget means that for a facility at distance, say 2 from the client, then the client has a budget of 3. So it can spend this budget by spending 2 traveling to these facilities, and then it has an extra budget of 1, and that's what he's willing to bid to open that facility. Okay, so that's basically the main idea. And then what happens is that when a facility has enough budget, okay, to have enough people bidding for it, then we will open it. Okay, and so when it opens, then the clients has spent their money of $1 to that facility, and now it's fixed, it's lost. He has given that money, and he's using these 2 remaining budget value to go and travel to this facility. Okay, and of course, when this happens, then any other facility, the client is not bidding to any facility that is further away, right? Because first, he doesn't have enough money left to reach it, so he doesn't want to pay for it. And also, it's bad because he doesn't want to travel more. Okay, okay, but the client is still gonna contribute to facilities that are closer, right? So if it has a facility at distance 1.5 that is already open, then among the 2 budget items that it's willing to pay, it can spend 1.5 to travel to here, and then it can spend the 0.5 remaining to open that facility, try to bid for opening that facilities because it's going to improve for it. The issue is that now when you try to do that for all clients at the same time and all and increasing the budget just a little bit by a little bit, like tiny amount by tiny amount, then it becomes very hairy. And the reasons are essentially because this algorithm is very adaptive. There's a lot of clients that are engaging with each other to open facilities. So if 2 clients agree to open one facility, then it changes what other clients can open because now they will decrease their budget. And then at the next round, clients will increase a little bit and so on. So it's a very intricate process where it's impossible to. It seems hard to apply this in parallel or in different. It's very sequential algorithm where one event can happen at any step basically. And also when you change the price just a little bit, and that's the issue for the bypass rounding, is that when you change the price just by a tiny amount, then you may actually decide that all these clients that had enough money to pay for it, they don't have enough money to pay for it. And actually what's happening is that other clients, some part of the clients may open something else, and it's becoming very difficult to account for tiny changes on the price. So a typical example is this, where you have, all of these facilities become tight at the same time. So either all these clients get together to open the red, or they all individually open the green, right? And you can go from one to the other, and it drastically changes the number of centers you will open at the end. So it's a very big challenge here. So what we have is a very adaptive algorithm here, where we're going to have only log-in phases, because we're going to increase the amount of the client's budget of the clients by 1 plus epsilon factor at each time, 1 plus epsilon squared. And then that leads us to log-n steps, log-n phase, where we increase the cost, the clients. And okay, and now we have a little bit of a challenge, because if you make this big bump, then you may have some facilities that are overpaid, right? Because the facility was almost paid, was almost ready to be open, and now we bump all the clients. Now it's too much money, and then the analysis is not valid. Like, we cannot do the dual fitting analysis that go with it, because the dual will not be feasible. Okay, so we have some tricks to deal with that, some ideas. So we scale down the metric so that we lose this 1 + epsilon factor in a reasonable way, and we relax the way we can open facilities. We can open facilities if they are slightly, they're close to be paid for. So then we can adjust the clients. And that gives us like this 2 + epsilon LMP algorithm that is less adaptive, that has only these log n phases. And then if you have these log n phases, then we can do this bypump rounding, right? Because at the very beginning, what I was saying is that we have this algorithm for facility location, then we run this algorithm with a slightly less price than the other one, like with two prices, one that are very close, but one smaller than the other, and one gives us slightly less than K, one gives us slightly more than K. And we do this binary search to find what's the right value of the price. And then we obtain a solution by walking from one solution to the other, which essentially makes the prefixes of solutions identical phase by phase. So at the very beginning, no centers is open, so those two solutions agree. Then at phase one, we will make some work. We have some algorithm that will convert the prefix of one solution into the prefix of the other, so that they agree on the prefix at step one, and then go to step two, do the same work, and so on. And at each step, we can do this walking between one prefix to the other by adding a few constant number of extra facilities. And that at the end gives us this log n extra facilities, because we are going to have one extra facility, or constant number of extra facilities per round. Okay, so that's the whole overview of the first algorithm, the 2 + epsilon, that gives us this. And then I can mention this theorem 2, which gives us a 2 + epsilon approximation for instances that are stable, for which like decreasing K by 1 increases R by a small amount. So what does that mean? So that means that if you remove a single center, then you increase the cost by somewhat significant amount, right? By opt. Like if you remove one center at random, you might expect to increase the cost by opt over K or something like this, right? Like if all the centers are the same. But here that's not the case. Like you will really hope to see an increase of like epsilon squared over log n increase in the epsilon over log n times opt increase in the cost. So that means that we have a bunch of clusters that are actually separated. Like most of the cluster in the solution are actually far away from each other. And so it's any constant factor approximation or any reasonable algorithm that you will run will correctly find most of the clusters except log n over epsilon squared, many of them. Otherwise, it wouldn't be a constant factor approximation, because that means that you will be missing drastically a lot of centers. The cost would be very high, because if you remove one, you are increasing the cost now. Okay, so now what we want is that if we can identify all but x many centers, and x is this log n over epsilon squared, then the goal for us is to get to 2 approx in time 2 to the x poly n. And that's why it becomes really much like an FPT algorithm, because we have these challenging centers to identify that would like to, figure out where they are. And for this, we want to do it in FPT time. Okay, and the idea is that there is this work by myself and some co-authors on ICOP19, where we showed that you can actually get a 1 + 2 over e to the 1.73 approximation in time log n to the k. So some sort of log n to the x poly n for this problem. So it's almost there, but if we go with this, that would be a quasi-poly time, right? Because log n to the log n, that's not what we want. And so I'll explain how to speed up what we did in ICOP19 mostly a lot of details, but like at the high level, to run it in 2 to the X Boolean. Okay, so basically the idea is that you have some leaders, and the notion of leaders is key. Is the set is a client P is a leader if it's the closest client to a center C of a opt cluster. So right, so you have an optimum centers of opt. The closest client is a leader for that center. Okay, so now if you had few clients, then you could guess who are the leaders because there are k of them. So it's k choose. So sorry, number of clients choose k. And then you can also try to guess approximately up to 1 to the 10 factor the distance between P and between the leader and the closest center. And that gives you some balls, and that's very helpful. I'll tell you why. But basically, the number of guesses you're making here is like some distances to the k and some number of clients to the k. And okay, and then you get the balls. And these balls, they tell you should open one center in each ball, but we don't know which center we should open, but we know and we promise that we will do it. And if you do that, if you try to solve that specific problem where I give you balls around leaders, and I tell you need to open one center in each ball, then output any center in the ball, you're going to get a 3 opt because the leader, by triangle inequality, you're going to pay at most 3. And selecting the optimal one gives you opt. And so basically, you can show that you will run some sort of modular optimization method or greedy method, and then you will get 1 plus 2 over E, which is optimal for this problem. So this is optimal, and that's what we showed in the iCal paper. The question is like, how do you speed up this process? So one of the key idea is to use desampling, which is a cute idea because it's using an algorithm that is using practice to solve a very theory problem. The issue is that one of the running time bottleneck comes from enumerating all of the possible leader choices. So even if you start with a core set of size k log n, you will still have k log n to the k log n choose k, which is k log n to the k possibilities for the leaders, and that's just too many. So that's not good. So instead, what we did in this paper is to start with a constant factor approximation, and then we are going to try to sample leaders proportional to its distance to already sampled points, or to the point in the constant factor approximation. This is the work of Arthur and Zalewski in 2007 for k-means. And so D-squared sampling, you will sample maybe 1 point, then another point, then another point, and then you miss some of the elements for sure. But if you didn't sample a point from an optimal cluster, and this is an expensive one, so sorry, if you have a cluster of opt that is contributing significantly to the cost of your constant factor approximation, then the probability that you sample it is like epsilon squared over x. And so now you have two options. So you make some x over epsilon squared samples, maybe times log 1 over epsilon. You push it a little bit, and then what you know is that you will be likely to hit all the expensive clusters, and the one that you didn't hit are either inexpensive or you are very unlucky. And that's fine. You can then charge it. You can say, okay, this cluster is fine. I missed them. I will just pay what I'm paying in the constant factor approximation. And the other one, I sample the leader or something good. And so the full overview is that you compute an R1 approximation, you guess the leader efficiently using this idea of using desampling, and you remove centers from A that are not in opt. So here there's a lot of work that I'm hiding at RAG, but like there's a lot of things you can remove some centers, and then you use this modular optimization because now you have the leader, so you have removed the center of the approximation that you didn't want, and then you can just do the ball argument that I mentioned. Okay, so let me conclude. So our result, so our main theorem is 2 plus epsilon approximation for k-median. which decomposes into two theorems, a 2 plus epsilon that opens k plus log n over epsilon centers, and a second theorem that says that you can get 2 plus epsilon for the stable instances. Now, of course, there are a few open problems. So the nice takeaway from this work is that you can open slightly more than k centers. It's fine. So basically, there is no gap between opening k centers in expectation or always. Like, you know, it's fine to think of k as a slightly more loose bound. And we know that it's hard to get better than 1 plus 2 over e, but can we get tight? Can we get it? Right? That's the main challenge. And the integrality gap of the LP is at least 2 if we have to open up k center, exactly k centers. What is the approximation, integrality gap of this standard LP? If you can open slightly more, like, to k centers in expectation. And I'm going to stop here, and thank you for your attention.